Hi everyone, I'm AJ Sheikh. I work for John Zink Hamworthy Combustion as a process engineer. I graduated TU in 2014 with a bachelor's in chemical engineering, and then right out of school went to go work for Zink. So for 5 years I worked in the process burner division designing combustion equipment for the process burner side. Now I'm working with gas processing, so if any of you are taking gas plant design, some pretty helpful skills you'll pick up there. That was a good course that I took. But today, we're going to just talk about fuels. What are fuels? Why do we care about fuels? Okay, this is going to be one of the easier lectures. I'll be back next week talking about combustion chemistry. We're going to go a little bit more in depth, but for this, we're just going to, it'll be a pretty nice overview. Okay. We'll go in more in depth next week. Yeah, important notice. So, learning objectives. What are we trying to target? So, understand the basic chemical equation for combustion. I bet 99.9% of you have already seen it. You know what's going on. That's a refresher. I want you to pay attention to it, though, because you're going to be using it over and over again to understand the chemistry behind what's going on in a combustion process, right? So give practical examples, domestic and industrial, of combustion processes. So we burn fuel and make heat to do a lot of things, whether it's in industry, whether we're processing chemicals, or at home, right? How do you get hot water? You have a hot water heater. There's a little burner in there that's heating it up. Cook something on the stove, you need heat. You can use a natural gas stove, or if you got an electric stove, that's coming from the power plant, and they're burning fuel to get you your power. Identify the difference between pre-mix and diffusion flames. So when we're designing combustion equipment, there are different ways you can go about mixing the air and the fuel, or the oxidizer and the fuel. Okay, we're going to go over two really important, two distinct methods of doing that, and it's really important to understand what the differences are for analyzing future combustion equipment. So not just burners, but if you look at flares, TOs, any of the sort, you'll be having to think about those principles. And then we have some key terms. So if you want to understand combustion and understand how to design combustion equipment, you have to speak the lingo. Right? What does it mean when I say LHV? What the heck is that? Adiabatic flame temperature? Has anyone heard of that before? It's important to know because it's actually pretty critical when you're designing combustion equipment. So we're going to go over some of the lingo. It'll be a pretty lean overview, not too in-depth. Next week, though, we're going to jump into the chemistry. We're going to really take a look at the combustion chemistry behind that because it's important to understand that as well. So, first things first. Heat is really easy to put on paper in a diagram. I can design my distillation tower and say, oh, I need a preheated feed. I need that feed heated up. Or I have a reboiler, right? And I need a boil up in order for my mass transfer to occur. So I need a reboiler that has heat input, okay? On paper, it looks simple. I got a little box and heat, right? Reality is there's a lot of engineering that goes into getting that heat, right? In order to apply that heat and heat up your process, there's safety concerns. You got to make sure that flow rates, pressures, temperatures, everything is running smoothly because you don't want to go outside of the bounds of your process, and you want to make sure everything is safe. So here's the inside of a vertical cylindrical heater that might be used to preheat a feed to a distillation column. As you can see, it's tough to see on the screen, but if you have the slides printed out, there's actually tubes of your feed going up and down, snaking up and down, all the way around the can in this heater. And you can see the burners in the middle are burning fuel, supplying heat. So it's not just simple of, oh, add heat. There's a lot of engineering and detailed design that goes into it. So keep that in mind, and that's what we're going to be trying to elaborate for you throughout this course. Okay, any questions so far? I think it's been pretty light. Okay. Let's take a look at some examples. Why do we burn fuel? Okay, or what fuels do we burn? So there's natural gas. If you have an industrial process like a feed preheater, sometimes your burners will be burning natural gas, okay, in order to release that heat and capture that energy into your process. Propane, right? Propane is used to run industrial processes as well. Also used to run your grill at home, if any of you like to eat barbecue. Gasoline, right? You put gas in your car. That's a mixture of hydrocarbons that The combustion reaction makes the pistons move up and down and causes transfer of that energy into mechanical energy so your car can move, right? And then you have waste gas. Waste gas is really important because sometimes you're running a process and you can't sell everything, right? You have off-spec gas that's not pure enough to sell to the labs or sell to whatever place needs it to continue to run their chemical reactors. You don't want to throw it away. You can't, it's really not great economics to just flare it and get rid of it. So you can actually recycle that and capture that heat back by burning it and using that to supply the energy to your process. Okay? Why is that important? If you design all your equipment for one fuel, but you have this waste stream that's different from the main fuel that you've designed for, the burner might not be able to be stable burning that fuel because different fuels burn differently. They behave differently. And when you're designing combustion equipment, you need to understand what those differences are. Okay? So you can make a safe and effective piece of equipment. And of course, why we care? Yeah, fuels, I think I said that one already. You got to make sure everything's safe and you got to make sure your process runs smoothly. You don't want to overheat your feed. You don't want to, for your mechanical engineers out there, metal has temperature limits you can expose it to, right? Sometimes we like to limit, let's say, stainless steel 304, stainless steel to 1700 degrees. We don't want to exceed that. Right? Well, if you're not engineering your combustion equipment properly, you can well exceed 1700 degrees and you can start melting stuff down. You'll have some mechanical failures. Okay, so now that we know why we burn fuels and why we care, let's take a look at the chemistry behind it. Okay, so you know, both sides of a chemical equation, you've got to make sure that the mass balances out. So whenever you're working with fuels, you look at the chemical equation balance. Okay, you have your fuel, and you need an oxidizer for the combustion reaction to occur. Oftentimes it's oxygen. There are other oxidizers out there, but you have oxygen. And just pure oxygen, is that easy to get a lot of the times? I mean, what do we breathe every day? We breathe in air. It has some oxygen in it, 21%, but the makeup is mostly nitrogen. So why is that also in the chemical equation? Well, it passes right through in the combustion reaction we're showing here at the bottom. But at really, really high temperatures, and we'll talk about this later, at really high temperatures, the nitrogen, even though it's inert, some weird things can happen when the temperatures get really high. Dissociation of those atoms can occur, and that'll create other radicals to appear. And those are important because some of those are toxic emissions, like NOx, nitrous oxide, contributes to photochemical smog, acid rain. If you have asthma, it's bad news. Even if you don't have asthma, it can be bad news. But the basic chemical reaction is something you should definitely understand, definitely for if you're designing any sort of combustion equipment, and of course for next week when we go into in-depth combustion chemistry. So you have your fuel. In this case, we have hydrocarbon represented in the first equation, plus oxygen, plus the nitrogen that's coming along with it because we're burning it with air. It's becoming, main products, CO2 and water. Okay, CO2 and water. Those are your main combustion products. And those get so hot in this chemical reaction that sometimes it starts to glow maybe an orange color, and you see something called a flame. Okay? And so that's what's going on. We're reacting these products, we're making heat, because we want to capture that heat and use it. Okay, basic hydrocarbons. What are we dealing with? Alkanes, alkenes, alkynes, cycloalkanes, aromatics, oxygenated hydrocarbons. We burn a lot of different things, mostly hydrocarbons. Sometimes you just have hydrogen to work with. You know, if you have a steam methane reformer, you're trying to make hydrogen to run a different chemical reactor, you're going to have to burn hydrogen. Hydrogen is weird because, well, does it form CO2 when you combust it? No, you can't because there's no carbon there, right? It also burns very, very hot. It burns very, very fast. So you have to have extra safety precautions when you're designing equipment around hydrogen because its properties are just wonky. Wonky compared to regular good old vanilla hydrocarbons. Okay? And we can burn all different types. Remember when I said waste fuel? Sometimes if you have a chemical reactor running and the off-spec product of that, it can have some really odd chemicals. It's not just simple methane, ethane. You can have alkenes, alkynes, et cetera, et cetera. So understanding sort of the lingo behind that. What's an alkene, alkyne, everyone? This is senior level elective. I'm sure you all know the difference. If not, look it up before next week. Understanding what we're dealing with is also very important. So we burn a lot of hydrocarbons. So let's look back. You have combustion, and in most cases you're performing that combustion because you want to capture this heat, you want to capture this energy, and you have to have a fuel and an oxidizer for that combustion reaction to occur. Okay? Did you all talk about the combustion triangle last week at all? Okay, we'll get into that. Well, you need fuel, air, and spark, right, to have the reaction propagate. If you see a flame, you're seeing combustion products that are so hot that they radiate in the visible spectrum, if you can see them. Sometimes it's still hot, but it's not in the visible spectrum, so you can't see it. But I guarantee you, anyone know why Everclear is called Everclear? Try to burn it, it burns clear, right? Well, it's radiating, it's hot, but you can't see it because it's on a different spectrum. That doesn't mean it's not hot. Industrial combustion. So you have to understand the reactions that are going on in the background because different fuels create different products. If I'm burning hydrogen, I'm not going to have any CO2. If I'm burning an unsaturate and I raise the temperature really, really high in my combustion process, you might have some polymerization even going on the burner tips, right? You can have a lot of odd mechanical failures that happen if you overheat a process. So understanding the differences between the fuels and why we're burning them is critical in combustion equipment design. So probably repeated myself on the same subject, so let's dig into the lingo. So how much fire do you need to run your process? What do we talk in when we're talking about energy input to the process? Well, there's a couple of energy units that we like to use because typically our processes are semi-batch or continuous mostly, so we talk about a heat rate to my process. How much heat do I need per period of time? And the most common one you'll see here in the United States, million BTUs, British thermal units per hour. That's kind of the gauge that we talk about when we're saying how much heat do I need to my process, million BTUs an hour. There's also the megawatt, which is 3.41 million BTUs an hour. That's what they use in Europe all the time. They also like gigacalories, which are the last unit over there. Slightly different from a megawatt, but you're looking at other ways to represent an energy rate, okay? But what does that mean to us? So I have some pictures here on the bottom that show some typical examples. Batch would be 100 BTUs an hour of heat release-ish, right? Not exact here. If you have an industrial burner, maybe a feed preheater to your distillation column, 5 million BTUs. Your stove at home, 10,000 BTUs an hour. How much energy is it putting out? So here's in a large plant, if you have a huge chemical process going on, 300 million BTUs an hour are required to keep your process running, to supply. That's how much energy you need to supply to heat your process to the right temperature. So it's a lot more than 100 BTUs an hour. You got a whole industrial heater with hundreds of burners firing a lot of fuel. And then you have a flare, right? A flare is a safety system for a plant. If you have an upset, you don't want to keep your equipment pressurized, or you don't want to over-pressurize your equipment. Because have you ever seen metal pipes burst? It's pretty scary, right? So these mechanical failures due to high pressure, we don't want that to occur. So we dump all that fuel to the flare, okay? The flare is the final safety piece that just burns all of that fuel so it doesn't overpressurize our equipment. And the heat release, it needs to be handled up to 10,000 million BTUs per hour, which would be 10 billion, right? So that's the lingo we're talking about when we're talking about heat release. Okay, the other thing we talk about is heating value, okay? That is the energy release per unit measurement of gas. In the United States, here's what the unit that I see all the time is I see BTU per standard cubic foot. Okay, BTU per standard cubic foot. And there are two ways to talk about it. You can talk about the higher heating value, HHV, or I can talk about the lower heating value, LHV. And you got to know the difference between the two because different industries use different ones. So commonly you'll see higher heating value used, and that's the energy release per standard cubic foot, or energy release per unit of fuel, if you took the combustion products, the water vapor from the combustion products, and you recovered so much heat out of it, right, with your heat exchanger, that you're starting to condense the water. You're extracting all that heat out of it, and you're condensing the water. And that's how much energy you can pull from this fuel. The lower heating value says, wait, you know, it's not really that realistic in all cases to extract all that heat because we don't want water on our tubes. We want it to exit as vapor. We don't want to extract all the heat out of those combustion products because we don't want to have to deal with water. So they use what's called a lower heating value when they talk about how much energy input and when they're talking about the heating value of their fuels. Okay? Now, you could have a standard cubic foot of, let's say, methane, right? And there's nothing different. Methane is methane. The higher heating value and the lower heating value are just different ways of looking at how much energy you can release. Okay? We like to use lower heating value in, let's say, process burners because we don't want to extract so much heat that we condense that water. So we look on fuels in general, lower heating value in the process burner industry. Boiler burners, flares, glass, steel industries, they like to extract a bunch more heat. So it makes more sense to them to look at the higher heating value of the fuel. Okay? Make sense? Good. So let's look at some higher and lower heating values of fuels. Methane, hydrocarbon, simplest one. Alkane, 909 BTUs per standard cubic foot. LHV. So if I'm in the process burner world, I'll be paying attention to the column all the way on the left. And then HHV is a little bit higher, about 10%. So there's a good back of envelope calculations there at the bottom. Okay? And there's just different fuels here. Let's see, propane. You can see BTU per scuff value is much higher, right? So per a standard cubic foot of propane, you're going to get a lot more heat out of that standard cubic foot than if I'm firing and burning methane. So can I just willy-nilly switch out, you know, I'm flowing a certain amount of methane to my burners, I'm running my process, and they're like, we're out of natural gas, can we just switch over to backup propane? Do I need to flow at the exact same rate? I'm going to be throwing in a lot of extra heat, and a lot of bad things could happen if you don't understand that there are differences between fuels. Okay? Ethylene, propylene, butylene. Another way you can look at the LHV is BTUs per pound. But we usually don't use that because usually we're flowing gases and we measure everything and we use the molar basis and look at standard cubic feet, right? So the yellow columns are more useful, but you can see there's a difference, right? One is on a standard basis, standard cubic foot basis, one is on a weight basis. And you can see if you go to, is hydrogen on here? Man, hydrogen has a really low LHV on BTUs per scuff, per standard cubic foot. That's what a scuff is. It's shorthand for scuff, but look at its BTU per pound. Its molecular weight is so small that on a weight basis, it packs a lot of energy. So that's important to realize. Just because you have a low BTU per standard cubic foot, it doesn't mean that it's not really, there's a lot of energy in there. There's potentially like a lot of energy if you store a lot of mass of hydrogen in a tank. So, understanding heat release, or heating values, how much energy per unit does a fuel release when you burn it? Any questions so far? Okay, good. So let's look at different fuels, because this is the fuel lecture, and talk about UFL and LFL. Upper flammability limit and lower flammability limit. Okay? Because, believe it or not, one of the most important things to keep track of when you're trying to design combustion equipment to burn fuels is that fuel actually going to burn with the fuel-air mixture that you have? So an upper flammability limit is the upper range of the fuel-air ratio that you can have so that it'll burn. Because if you add too much air, if you use too much fuel, you can't burn. The mixture is not flammable. If you have too little fuel and too much air, conversely, right, you also won't burn. You have to be in a range, and that range is different depending on the fuel. You can see hydrogen. Remember when I said hydrogen really wants to burn and burn fast? Look at its flammability range. 4 to 75% of hydrogen in air. Okay? And then if you look at methane, it's a different range, 5 to 15. It's a little bit harder to burn. You look down there at carbon monoxide, CO. Man, it's easy to burn carbon monoxide. Okay? So I think there's a little scenario here at the bottom of is a mixture of 1,000 cubic feet of methane and 8,000 cubic feet of air flammable? Let's check it out. Find the percent fuel in the mixture. Okay. You have 8,000 and 1,000. That's 9,000 standard cubic feet of stuff. And so your concentration of fuel is 11%. And you can take a look at your handy-dandy little chart and say, is it flammable? Well, the flammability limit is 5 to 15%. Is 11 in between 5 to 15 not a trick question? Yes, good. Head's nodding. So it's flammable in that range. So if that concentration was less than 5 or greater than 15, it wouldn't burn. And you'd just be throwing fuel out there, and you're like, oh, why isn't there any heat going to my process? Why am I filling my box with a bunch of unburnt hydrocarbons? Oh, man, I've created a bomb. It's important to understand that different fuels have different properties. And if you have a mixture of fuels, let's say 50% hydrogen and 50% methane, you can't just average the flammability limits. There are mixing rules based off of Le Chatelier's principle. And they're in your combustion book. I think everyone's getting a copy of the combustion book. I like to stick one of those questions on the test, on the first test, but it's pretty straightforward. You go to like page 75 in your book and follow the directions. But just heads up. Okay, so this is your first homework problem. I'll give a summary of all these at the end. But what happens if instead of burning methane, I swap to propane? Okay, same ratios. I got 11% propane in air. Is that going to burn? It's not a trick question. It's pretty simple, but just to check if you were paying attention or sleeping, that's your first homework problem. They're on the slides. The slides should be uploaded. Whoops. Okay. Pretty simple so far.
Just a heads up on that. I still don't have access to Harvey, so as soon as I get that, I'm waiting for them to give me that access. So it's not on there yet.
Okay. It's not on there yet. It's coming, though. Don't worry. We'll not make the homework due until, say, so I'm coming back next Tuesday. We'll, like a week. Whenever it gets up, we'll give you all plenty of time. They're easy questions. We'll take 10 minutes. Okay. So pretty simple so far. Fuels are different depending on which fuel you're working with, and they burn differently, and the safety precautions behind them are different. But also how you mix the fuel in the air has a big effect on your combustion process. So there's two main strategies we use when we're mixing fuel and air in the combustion industry. Okay, number one is I wouldn't say it's the most common, right? Because I see a lot of diffusion flame processes out there. But one way of doing it is to pre-mix the fuel in the air. Like your Bunsen burner, right? In your lab, you hook it in, and you got your fuel supply, and then you have an opening in the bottom that pulls in the air, and it mixes, and then it burns right there on the tip, and you can heat your Chem 1 water for your experiment, right? You're mixing your fuel in the air ahead of time before it burns. And that's the picture on the left. We have a pre-mixed pilot flame where down through a tube I've taken my air and my fuel, just like a Bunsen burner, a little bit different. There's some stabilization mechanisms and geometry intricacies going on the inside that we can talk about later. But I'm pre-mixing my air and my fuel, and then I'm letting it burn. Okay? Notice how it looks visually. The next thing, if you have just a candle, you have wax, right? So you lit your match and you started your candle, and that heat that you started on your wick is actually vaporizing the wax, and you got your vapors flowing up. But you didn't pre-mix the oxygen and the fuel. What's happening is that the air that's surrounding here on the outside is diffusing into the fuel until you get a burnable mixture, and then you see the nice little lazy flame you have right there. Okay? Notice the differences. Here's a nice little diagram to look at. So if you have a non-premixed flame or diffusion flame, you have zones. You have a lot more zones of combustion, okay, because the air is having to diffuse in. Or if you have like a typical process burner that has the fuel, air coming through the throat, and you're shooting the fuel in, you can have a core of air and the fuel is going inwards, right? It doesn't matter if it's in to out or out to in. It's diffusing, so you have zones of combustion that have different temperatures, different stability mechanisms, right? Different levels of pollutants you can make, depending on what you choose and on how to mix it. Opposite for the premixed flames, right? You have the premixture right there, so usually you have a nice and tight flame, less zones, less of that gradient, right? So why don't we just stick with one versus the other? That's probably a big question that's on your mind. It's like, okay, you have these two strategies. Which one do we pick? Well, it depends on the fuels you're burning, right? A lot of times premix flames, they can create, if you get the ratios right, they can create some low emissions, and you can create really short flames, which is good because if I have a process tube here, if I'm directly impinging on that process tube, I could overheat it very quickly and bust it open, and that's not good, right? So I can make a nice compact flame, but there's a concept called flame speed, right? And if your flame speed is too fast and you have a combustible mixture all the way through the pipe leading up to the premixed combustion zone, you could flash back all the way to a fuel source. That's not good. Or all the way to back where you're mixing the air and the fuel. With the diffusion flame, all your air's out here. You don't have a combustible mixture in the tube. So there are some safety aspects of it that are easier to control. So you can't just choose one or the other nilly-willy. You have to analyze, what are my mechanical constraints? What fuels am I burning? Because different fuels burn at different rates. Flame speeds, adiabatic flame temperature, those are all very important, as we'll see in a second. But the main two ways we go about it, depending on the application, right here. Premix and diffusion flame. Okay, let's talk about flame velocity. Going too fast? Any questions so far? We're good? Okay. If anyone has any questions in the slides, ahmed.sheikh@jonesinc.com, just email me. I'll answer you back. It's not like I actually do work in the office. You didn't hear that, Doc. So you have a mixture velocity because you have this. You might have a fuel-air mixture, or you have this just fuel mixture coming through, or just air velocity. But you have a mixture velocity, a fuel and air eventually, right? And the flame, because a combustion reaction is hot, it's wanting to propagate backwards at a certain speed. Okay? And what we want to do is we want to create a stationary fuel front. So when we design our equipment, we want to make sure to have the geometry correct and also the fuel-air ratios correct in order to keep the flame stable and stationary. We don't want the thing moving out and in and out and in, because if you create a resonance, it could easily become unstable, right? If you have something that's really odd and harmonic, if you something else, someone walks by the heater and sneezes, that could throw off the entire resonance, and then all of a sudden you're no longer stable. So you got to make sure you try to hold a stationary flame front. And what do we have to look at? Well, a big thing that affects that is the fuel you're burning, right? If I'm burning hydrogen, well, flame speed is fast, really fast. If my fuel-air ratio is off, well, that affects your flame speed. Your fuel-air ratio will affect how you need to make sure your combustion equipment is designed. So, key point is, you got to understand what you're burning. You got to understand how it interacts with the air and the fuel. Otherwise, you will do something not safe. Okay, so let's look at differences. Flame speed, hydrogen versus methane, propane, and other hydrocarbons. So you can see that hydrocarbon flame speed is relatively low compared to hydrogen. Look at that. Look how much faster it is. Laminar flame speed in centimeters per second. Now, there's a very important distinction that we'll go into more next class. Okay, laminar flame speed. If I have a laminar mixture of fuel and air, its Reynolds number is very low. How fast is it going to be propagating back? Because when you start adding high pressure situations in there, or high velocity flows where you're turbulent on the inside of the pipe, the laminar flame speed does not exactly correlate to the turbulent flame speed in a way that's very intuitive. It's actually a little bit complicated to analyze your distance, where you're at in the pipe, and the flame speed at different parts of the pipe depending on the mixture. So just disclaimer, laminar flame speed is like the simplified version of flame speed. And a lot of times we don't deal with laminar flame speed. But the basic concept is still there. Hydrogen burns really fast. Propane, methane, not as fast, but you still got to consider the flame speed. And down there, the fuel-air ratio affects it as well. You can see the peak occurs, well, does the peak occur at stoichiometry for both hydrogen and propane? No, it looks like the peak occurs at somewhere between 1 and 1.2 equivalence ratio. So if you have a little bit of extra air in there, it'll burn faster. And for hydrogen, it's not its peak point. The more air you add, the more and more and more it'll want to burn. So different fuels behave differently. And that's really the whole point of this lecture. I can just go to the end and let you all go now, right? No. Okay, why do we care about flame speed? Like we hinted at before, stability of a burner. Right now we have a burner that's really designed to fire hydrogen and natural gas. So that combustion mixture, that combustible mixture, has a certain flame speed. It has certain heat release properties. We've really designed the burner well around that. What happens when you throw in a bunch of nitrogen? Okay, remember, natural gas is a little bit harder to burn. Can you burn nitrogen? No, it's inert. It's inert. So I've totally thrown off the flame speed and the adiabatic flame temperature and the fuel properties and characteristics of this flame. And does that look symmetric, stable, and do you want to go into look into a heater and see something like that? No, because this side is burning good, but the other side, instead of combusting the fuel and creating non-combustible flue gas products, we're just shooting fuel in a box. And that can be very dangerous. You want stuff to burn, and you want to create CO2 and water. You don't want to just let gas fill up a room or a box or a furnace or whatever your process is, or a heat exchanger. So flame speed, you might not want to premix if there's a bunch of hydrogen, because hydrogen wants to burn fast. And instead of burning on the outside, like this is what's called a radiant wall burner, that flame is supposed to shoot out and attach onto the wall. Instead, it's burning right there at the tip, and any minute, if you disturb something, it could go back into the tube and flash back to the source. Not the safest thing. It's very loud, too, if you've ever heard it in the field. It's not a fun process. So that's why flame speed is important. Okay, next concept. I'll let you all finish taking some notes on flame speed if you have to do that. But now we're going to talk about how hot is a flame. Okay, really hard to calculate, because usually when you have a flame in a box and you have a process, you're trying to transfer that heat to the process. Okay, and when that's occurring, the temperature gradient that's going on there can be different depending on a whole many different factors. So what we do is we look at something called the adiabatic flame temperature. Now, the adiabatic flame temperature is a theoretical temperature. If in your combustion products, all that heat that you've released, instead of being transferred to the environment, it's contained within the combustion products. And there's no heat transfer or work in or out. As if I took all that heat and concentrated it onto my combustion products, what's the temperature of that flame? What would it have been? Okay? As you can see, it's really hot. Methane, if I took all that heat and I concentrated it without letting any of the heat escape, it would be the combustion products. I think this is all at stoichiometry, by the way, because your adiabatic flame temperature changes if you start throwing in extra air and nitrogen. But it's 3,500 degrees-ish. Propane is even hotter, almost 3,600. You can see as we get down to the bottom, we get to hydrogen. Hydrogen is a weirdo in there because it burns fast and it burns hot, very hot, which means it's easy to continue to propagate the reaction. Now, anyone ever hear of an oxygen acetylene torch? It's what they do, if you have your AC unit and someone's welding together the copper pipe on the condensing unit, like they'll have an oxygen acetylene torch to melt the solder and weld the pipe together. That's because acetylene burns, its adiabatic flame temperature is really, really, really hot. Okay, the energy that it releases divided by the combustion products that it also makes, the overall temperature is higher. Okay, it doesn't create a lot of combustion products and it releases a lot of heat. So you got a lot of temperature to melt things and fuse things together. So don't treat all fuels the same. Why else is it important? Well, besides affecting stability, remember when I said those nitrogen molecules could split apart and do really funky things? Well, when you're running a reaction, when you're running a reactor, let's say our combustion system is a little mini reactor here. When I'm running it at 3,500 degrees, adiabatically, the chemistry behaves, all of a sudden there's enough thermal energy in there to start causing all these weird side reactions that you would never get in a low temperature system, like room temperature, right? 3,500, 4,000 degrees Fahrenheit, that's really hot. So you can get molecules splitting apart, like nitrogen, and they can reform into pollutants that we don't want to breathe in. NO is one of them. And really quickly, if you release NO into the atmosphere, it'll try to find the ozone and grab an oxygen off of that and create NO2, because NO really isn't stable in of itself. So we don't want to be throwing NO and NO2 out in the field. Well, high flame temperatures might be really good for, I can be pretty lazy on my combustion equipment design, because it's like, I know that fuel's going to burn, fuel temperature is really high. But if I don't spread out the peak temperature of that flame, I can create a lot of pollutants, and that's not good. I mean, there's statues. Have you ever seen the statues eroded away from acid rain? Well, that's because you're releasing a bunch of chemicals and creating acid rain, nitric acid falling down. That's why we care, because not only do we care about safety, process stability, but we care about what we're doing to the environment. How much bad stuff are we throwing out there? Some things NOx contributes to. Photochemical smog, really bad if you have asthma. Ozone depletion, remember that NO is not really stable. It likes to become NO2. It likes to grab that extra oxygen. Acid rain, so it can form nitric acid. And of course the greenhouse effect, retaining that heat. Yeah. Okay, so flame temperature, we want flame temperature because we need the combustion to be stable. But we'd like to lower it down some because we don't want to create pollutants. So what can we do? Well, we can dilute the fuel with air. This is why I said pre-mix can have a different level of emissions than the diffusion flames, because you have a really good, well-mixed mixture coming out and combusting, right? So you don't have peak flame temperatures. Okay, your energy is nicely divided up amongst your combustion products. You don't have that core. Well, you have a core in both cases, but you don't have these zones of hotter combustion and zones of colder combustion. Because when you have peak flame temperatures, that's when you create the most pollutants. If you lower the peak flame temperature and even everything out, at the lower temperatures, the NOx can't form as readily. The nitrogen can't split apart as readily. So you can dilute the fuel with the air. You can start pre-mixing. You can also mix inert gas. Remember when I said they threw in that mixture of nitrogen with that hydrogen, or with that natural gas in that burner? And it looked really wonky. That's because they added too much. But one way you can reduce the adiabatic flame temperature is to throw in some inerts, right? Because it's inert. It doesn't release energy, but it's still there. It's carried on through in the combustion. So all that energy is divided up amongst more combustion products. Okay, so you have a lower overall adiabatic flame temperature. Okay. And these are the type of things we think about when we're designing combustion equipment. Okay, how about the summary? I think we're done a little bit early. So, summary. Remember when I said there were key terms that you have to look at? Well, here's the lingo. Here's the acronyms we love. One that may or may not be on there is standard cubic feet, SCUF. You'll hear that a lot. But LHV, HHV, heat release, LFL, UFL. So a random assortment of just conceptual questions about these key terms. Those will be on the first exam, but it's open book, so you can look it up. Sometimes I'll put what I think is a very small curveball in there where I make you think, but that's usually only for 1 or 2 questions because you don't have unlimited time to do it. So don't worry, if you paid half attention at all and do the homework, you'll be fine for the exam. at least for my section. Other people write the other sections. I don't have control over that. No, we tend to be nice about that. A biggie there at the bottom, adiabatic flame temperature. What happens if you took all that energy and theoretically shoved it into the combustion products that you made? How hot would that be? And that's how we gauge, quote unquote, how hot a flame would be. And then we base our engineering, we can base a lot of our engineering concepts off of that. Okay, yeah, we'll get a copy of the slides. Let's just look at some examples on why this is important. So I have a burner, and I'm trying to, I need 10 million BTUs an hour. What's million BTUs an hour? It's an energy rate. So we're talking the lingo. That's how much energy I need to my process, okay? And the fuel, the little waste gas that I have off the side, it's 80% methane, 20% propane, and there's its averaged out LHV. In this case, the mixing rules are really easy for LHV and HHV. And so you're flowing through 8,400 standard cubic feet per hour, scuffs an hour, or pounds per hour, but nobody thinks in that because nobody does. And the fuel composition changes. So I'm humming along and I'm burning, and then all of a sudden I change the fuel. Not only does this affect can this affect the stability of the burner, but you also have different delivery pressures required to push that fuel out of the tip of the burner. Okay? Because usually you'll have a fuel tip and there'll be a hole in there, right? Or several holes. And the pressure, the fuel flow rate is determined by the pressure behind it and the size of those holes. So if I switch to a fuel with a different molecular weight, the fuel flow rate is going to be different at a different pressure because my molecules are shaped differently, and now I can fit more through the same size hole at the same pressure. So what will happen is the fuel flow rate will change if I keep the same pressure, but here's a nice little summary of what happens if you start changing fuels. In order to keep a constant 3.2 million BTUs an hour, I changed my energy rate on you. I'm sorry, guys. For all these different fuels, you need a wide range of pressures. So we don't put really fancy fuel flow measurement on a lot of the smaller pieces of combustion equipment because it becomes cost prohibitive, right? It's great that you have a burner that can burn all this fuel, but it costs $1 bajillion per unit, and I'm only making this much when I'm processing a barrel of oil, so I'm not going to buy your combustion equipment. Money is a real thing, like it or not. So what will happen is that we can calculate the fuel flow rate based on the fuel pressure. So if you don't know what you're doing, and you say, oh, we've switched over fuels, oh, before the burner was running at 5 pounds of pressure behind it, and now it's running at 3.7 pounds of height. I need to kick it back up to 5 pounds. No, your fuel's changed, so you're actually going to be flowing a lot more than you think, and your heat release has changed. You can throw a lot of things off. So it's really important, really, really, really important to understand what fuel you're running. Okay? Does that make sense? Your molecular weight is different. Your compressibility ratio is different. Your molecular properties are different, so you need more or less pressure to push the same amount of gas through a hole. Okay? And no, we don't design, in most cases on the process burner side at least, we don't design any sort of variable orifice. You don't have magically changing holes. So you got to understand how much pressure you need to flow a certain amount of fuel. Now there are variable orifices that are in there where you screw a screw in and there's a needle, but they're a pain. They can fail. We like to have stationary bits of equipment if we can out there because anything that can plug up, gum up, it's not good. These things have to last. Okay, let's just look at how. That was most of the content. We're just looking at pretty pictures of flames. So there's 100% propane. It's a nice little orange ball of fire right there. It's radiating at differently, and the mixture properties are different for this heat release. So if you have less pressure in order to flow a certain amount of fuel, the mixing properties are also different. How fast you mix with the air is different, and that can affect stability. So 100% natural gas looks pretty clean. Start throwing in some hydrogen, propane, and natural gas, and it doesn't really look like a mixture of these two, but kind of. You can see the orange streaks in there and the blue. Getting a visual feel for how a flame should look can be really helpful. Really what you want to look for, though, because different fuels, different burner technologies, there's so many different burner technologies out there. There's not a handbook that says this is how you look at a flame and for sure know that it's good or bad. You really want to look for stability. You want to look for oftentimes symmetry, right? And it should stay steady. If everything's tuned correctly, it should be steady. The flame should be moving in and out and lifting off and coming back down. You want things to be nice and stable and steady. So that's the biggest visual indicator I like to look for when I'm analyzing or if I'm out in the field looking at burners or any combustion equipment. Okay, summary of the homework. Go find some natural gas compositions, because when I say natural gas, what does that mean, right? I'll give you a hint. In Tulsa, it's going to be 90+% methane. If you go to Thailand and get Thai natural gas, well, they use enhanced recovery. Tell me a natural gas source. I'm not going to tell you that story. In Thailand, I'd be giving away question number 2. The way they get their natural gas is a little bit different, or the way they do something else is a little bit different, so your natural gas has a different composition. It has more inerts in it. If you go to, I designed a set of burners. We originally sold this to a company in Trinidad and Tobago in 1962, so it was way before I was born. But that equipment was bought, and they say, we have this different natural gas because we've moved all this equipment to Pakistan. And now we need you to take the same burner and make it run on our natural gas, which had up to, 30, 40% CO2, had 10% nitrogen in it. And I'm like, yeah, you can't just flow it. You have to redesign the tips. So we did a lot of testing. We have a test furnace at John Zink where we can design equipment, put it in the box, and fire it up and let it go. It was a really long, intensive project, but it was fun too. So yeah, not all natural gas is the same. Tell me natural gas source. How do we get natural gas? Do the LFL, UFL problem in slide 14. Follow me, subscribe on Twitch. No, I don't. So when I was in college, your guys' age, I think League of Legends was season 2. I don't know if anyone still plays that anymore, but yeah, I'm the anime video game guy at the office. So I round out all the sports people. I think the only sports thing that I like is the UFC, but here you go, homework problems. Some good sources for you if you need them. Your textbook, North American Combustion Handbook, Combustion Science and Technology, and Combustion with Flame. So if you guys have any questions or anything, or first of all, any just questions in general, maybe about what I do or any burning questions, no pun intended, in the back.
How did you get in the John Zink Institute and start teaching?
How did I start? Repeat the question. Okay, so how did I get into the John Zink Institute and start teaching? Well, number one is we hold combustion courses at the company, right? Where we take industry professionals and bring them in, and they'll come and they'll take maybe a week-long course about a very specific topic, right? As part of the design group, right? Sometimes you get to teach those courses. So I saw that, hey, there's an opportunity we teach courses at John Zink. I would like to get a shot at teaching one of these industry professional courses. And I guess they thought that I did a good enough job, so they asked me to come back a couple times. So really it's just, I communicated to my supervisor and Dr. Bockel over there, he's in charge of the institute. So I was like, I like to give presentations. This stuff is really interesting, and I think I actually learn a bunch by teaching. Give me a shot. And they did, and I'm still here. So that's how you do it. If you want something, communicate it. Pretty good advice in general. Yeah. Okay, anything else? All right, I think you guys are out this early. Appreciate it. Thank you. Email me if you have any questions.
If you haven't already done so, make sure you sign the sign-in sheet.